Hey there, Iron Designer here. So I wanted to bring you a video talking about how you can use Microsoft Excel or really any spreadsheet that has graphing capabilities and that type of stuff to do analysis and basically doing equation integration even when you don't know exactly what the equation is, or you can estimate the equation from your graphs or your data collection. And you need to integrate that equation because either you need to determine the energy, the power, the mass, or any other engineering factor that you need to take into consideration, and you need to integrate it, but you're not really sure how to integrate an equation you're not familiar with. So let's take a look at Excel and see what Excel can provide for us. So here at Iron Designer, we do a ton of reverse engineering work, and many times we do not start from a blank sheet of paper. We start from existing technology that has been lost through time. Maybe it was developed 30 or 40 years ago, and a company has bought the intellectual property rights and wants to reverse engineer how this technology was built. So here I've prepared kind of a spreadsheet to sort of illustrate this concept. Now, in the corner, you can see the equation is the very simple y equals x squared equation, just so we have a starting point. And usually from this equation, as you remember from your algebra class, you can generate y with various inputs of x. But likewise, if you already had a table of y values over time, or distance, or energy, or mass, or signal strength, or intensity, you could reverse engineer back out the values for x. And so what I've prepared here is just this simple spreadsheet, and I've taken 10 slices on y equals x squared. Okay, so the concept here is on your first pass, let's say you're reverse engineering this data, and you took 10 data points, 10 slices of data. But on the next pass, what I did here is I took 50 data points of data. Now again, I'm just using this as an example, so keep in mind this would be an approach of reverse engineering. So I've got 50 data slices on the second pass. And at the bottom, in each case, I'm summing up the areas underneath the curve. And I'll show you the graphs in just a second. And right here, this would be the 10 slices summation. The next attempt is 100 slices through the data pass. And again, just computing the areas under the curve by taking one value and subtracting the other value, equally spaced, and multiplying it times the height, exactly the way you're taught in class. So what I've done here is just to show the difference in the graphs. With 10 slices, you have a more jagged graph. And then with 50 slices, the jaggedness is cut down by a fifth. So you have 5 times more data points, so your jaggedness is smoothing out, correct? And at the bottom of the graph, you can see the span is from 1 to 2, and the rise is from 1 to 4 in all the cases. Okay? And then the final graph is the smoothest graph, which would be, say, the ultimate ability of your measurement system. So the ultimate, say, memory of your data acquisition set, or the ultimate ability to record. Say in this case, for example, only is, say, 100, but the span across the bottom is from 1 to 2, and the rise is from 1 to 4. So let's start looking at the analysis portion now. So what I've done here to the left column is just summarize and begin doing the analysis. So first of all, in the green color, the sum of the 10, the area under the curve was, say, 2.485. And then the sum under the 50 was 2.3634. And for the 100, the sum gets tighter. It's 2.34835. And what I did here is just show you that if you would normally just integrate this equation, everybody knows how to do that. But what we're doing here is we're reverse engineering based on what we understand. We're trying to approach a different problem, a more complex problem, using reverse engineering from data that we've collected, but we don't have the input function. We don't know how to graph the data yet. So we're looking at what the probability is of modeling the data and trying to fit the curve without actually knowing what the curve looks like. So we know the true value from normal integration of this y equals x squared, again it's an example only, is 2.33667. And we're going to say that the true error between the actual integration and the highest ability of your ability to record the data is an error of 0.015. Now, we of course always want to run a kind of a sanity check. So we know that the best approximation of our data using a linear curve would be sort of a triangle sitting atop of a rectangle. If you go back and look at the graph, you have a triangle that has a base from 1 to 2 and a side from 1 to 4, and then that's sitting atop of a rectangle from 0 to 1 and from 1 to 2. So if you do a sanity check calculation, the area under that curve is 2.5 if it was all straight lines. So we know that our data needs to be below 2.5 as a sanity check. If we had a number 2.6 or above, then there's some error that we haven't detected yet. So in our measurement data, we need to be below 2.5. And when we look at our estimations, even with just 10 slices through the data, we see that the worst number is still just 2.485. So now, with our 100 measurements, we look at a 1% error band. and use that as our tolerance, that we're believing the probability is that we're at least 95% confident or 99% confident that the true value is going to lie within plus or minus 1% of our computed value from our measurement. And so we have this computed tolerance in yellow, but this is based on the lowest value that we achieved and taking 1% of that value. So it's 1% of this value here. Using that, we are computing the error high and the error low. And so our probability is that the true value lies somewhere between the error high and the error low, without us actually knowing what the true value is. In order to obtain the true value, we'd have to do thousands of additional recordings of measurement. So finally, in this exercise, what I've written here in the notes is that from the measurements you've taken from the highest possible degree of accuracy, precision, and measurement that you could obtain with your measuring system, you have obtained the data that you are hoping the true value lies somewhere between the tolerances that you've recorded down. And this is the best obtainable measurement system that you can present in your report. And it's based on reverse engineering. So you don't know initially what the design history is of this product or how the early on concept was derived. You don't have any of the prototypes. You just have a final product, maybe a small sample size. You're running measurements on the sample, and you're attempting to reverse engineer what the true value is supposed to be for the product. Say, car battery. Everybody says it's 12 volts, but it's sometimes 11.9, sometimes 12.1. So you are trying to establish an error band around the true value without knowing at all what the intention was when they designed the car battery. You don't know that the actual value you are looking for is 12 volts. So anyways, this is Iron Designer. I hope this was helpful for reverse engineering and engineering integration. And this is Iron Designer saying we're out of here. Have a great day. So I hope that video was helpful. Reverse engineering is a topic that is not taught in school, but it is applied by engineers every day, especially in the line of work that we do. And if there's some topic you'd like for Iron Designer to make a video about, please put your topic in the comments below. And if you have any questions, please put your questions down below and I will try to get an answer out to you. Have a great day.